And we'll go straight into it. The equation for the decomposition of hydrogen peroxide shown below. Explain using oxidation states, oxidation numbers, why the decomposition of hydrogen peroxide can be classified as a redox reaction. Well, let's go through and assign oxidation numbers, shall we? First one, every atom gets an oxidation number. Second one, the total oxidation number equals the charge. Now that means, of course, that if we look at O2, there's no charge on O2, so the total oxidation number is 0. We've got 2 oxygens, so 2 of the oxygens must be 0. Thus the oxygen itself must be 0 in O2. Now we keep going, and we have no metals in anything. We have no fluorines, but we do have hydrogens, which are going to be +1. So if we have hydrogen is +1 here, well then we look at this and we'll say all that's left is the oxygen. 2 times +1 for the hydrogens plus 2 times the oxygen is 0. So therefore the oxygen must be -1. It's one of those special cases with oxygen, which is why oxygen is the 4th one in my list of assignments, because metals can make oxygen do things it doesn't want to. Fluorine can make oxygen do things it doesn't want to, and hydrogen in hydrogen peroxide can make oxygen do things it doesn't want to. Now let's continue on, because we still have water to assign, and I'm going to do that slowly now, but for the rest of the time we'll just slap it in where we see it. The hydrogen is going to be +1. We got 2 +1s, and the oxygen therefore must be -2 to cancel out the +2 from the hydrogens. So let's see what we've got, shall we? We start off with oxygen being -1, and some of those oxygens go to 0, so going from -1 to 0, the oxygen is oxidized. However, some others of those oxygens at -1 turn into oxygens at -2, which means that they have been reduced. So oxygen in the peroxide is both oxidized and reduced. It's called a disproportionation, but particularly answering this question, it can be called a redox reaction because you have an oxidation and you have a reduction. Now we got the ion electron half equation, whatever the heck that is, ion electron, I guess, for the oxidation of ethane di-O8. Ions is shown below, otherwise known as oxalate, much nicer number. Give the oxidation states for carbon at the start and the end of this reaction. Well, we know that we got here total oxidation number is the total charge. We got carbons, we got oxygens, there's no metals, there's no fluorines, there's no hydrogens, so the oxygen will be -2. Putting all that in, 2 of the carbons plus 4 times -2 for the oxygens is -2. So therefore 2 times the carbon is +6. This of course becomes -8. Bring it over there. 8 minus 2 is +6. So the carbon must be 3 in the oxalate. And now let's go to carbon dioxide. Again, no harm in saying the oxygens are -2. So the carbon plus 2 minus 2s is 0. Thus the carbon must be +4. So the oxidation state at the start for carbon +3 and at the end is +4. So this is a redox reaction. Let's see what we got. First thing is looking at the Cl2. We can say that the total oxidation number here has to be 0. So 2 times the chlorine is 0. So the chlorine itself is 0, element in its natural state. We also see we have water. Well, water is +1 for the hydrogen, -2 for the oxygen. Now, no metals, no fluorines, so the next thing we have is hydrogen. So there's hydrogen there and a hydrogen there. This one's easier to do because there's only hydrogen and chlorine. So the hydrogen +1 plus the chlorine is 0, so the chlorine has to be -1. Notice we don't have anywhere where it's like memorize what chlorine can be, because it can be -1, 0, 1, 2, 3, 5, 7, but we can get it from the context. And so in this case, the chlorine obviously -1. Next thingy that we have with hydrogen in was the HNO3, so let's pull that out and have a look, shall we? The oxygen is of course -2 because that's the next in the list. So we've got +1 plus the nitrogen plus 3 minus 2s is 0. So that means the nitrogen has to be +5. Okay, this of course becomes -6. +1 becomes -5, so the nitrogen -5 is 0. Thus the nitrogen here is +5. Moving on to the only one left, the NOCl. Again, oxygen's going to be -2, so let's pull that out, see what we got left. So the nitrogen, -2, plus the chlorine is 0. Oh no, what do we do here? Well, this is where we invoke rule 5. We say, well, we've got nitrogen, we've got chlorine. Chlorine is more electronegative than nitrogen, thus, so that means that chlorine is going to be negative. Now, what does chlorine want to be? Well, of course, it wants to be -1. Okay, we've known that ever since, whenever. No reason why the chlorine can't be -1, so that means that the nitrogen, -2 minus 1 is 0. The nitrogen here has to be +3. So showing this is a redox reaction, let's have a look at what we got. Hydrogen all the way through is +1. Oxygen all the way through is -2. But the nitrogen goes from +5 to +3. Thus it is reduced. Oxidation number, oxidation state goes down, is reduced. And the chlorine, some of them go from -1, not to -1, that's boring, but from -1 to 0. So therefore some of the chlorines are oxidized. Thus it is a redox reaction. When sodium nitrate, the sodium nitrate is heated, it decomposes, giving us sodium nitrite and oxygen. Use oxidation numbers to complete the following in this reaction. Blank has been reduced because its oxidation state has changed from blank to blank. Well, let's go ahead and see what we have, shall we? First thing we encounter is that the oxygens there, 2 of the oxygens are 0, so therefore the oxygen there must be 0 itself. Continuing on in the rules, we finally see a metal. So the sodium is +1 and +1. No doubts about it. You see a sodium in there, it's +1. Now then we continue on, no other metals, no fluorines, no hydrogens, so we get to oxygen. Oxygen has got to be -2. So let's pull that out first of all with the sodium nitrate. We've got the sodium +1, the nitrogen we don't know yet. 3 oxygens each at -2 is 0, so the nitrogen is +5. That's the same calculation as we had for the previous question. Now let's pull out sodium nitrite. Again, sodium's +1, don't know the nitrogen. 2 oxygens here, so 2 times -2 is 0. So we got +1 minus 4 gives us a total of -3. So the nitrogen -3 is 0. Thus the nitrogen is +3. So putting this in, what has been reduced, what oxidation number has gone down, is the nitrogen. So therefore, in this reaction, the nitrogen has been reduced because its oxidation number, wow, that does your eyes in, doesn't it, has changed from +5 to +3. Question 5, again, we got a nice little reaction. Iron 3 oxide, Fe2O3, carbon monoxide, give iron and carbon dioxide, give the equation for this reaction, and explain why it is described as a redox process. And it gives us this to start with, but you can tell it is not balanced. Okay, we got 2 ions there, so we have to have 2 ions there. And we've got 3 carbons to go with the oxygens there, because we got 3 CO2, because each time the reaction happens, you need one of the oxygens going from the CO to give us CO2, so therefore we need 3 COs to 3 CO2s, because we've got 3 oxygens there. So that was sort of baby balancing. Now let's go ahead and explain why it's a redox process. So we got to assign oxidation numbers. Well, the first thing is there's iron, charge of 0, so its oxidation number is 0. We got metals, but this is a transition metal. And transition metals, because they have variable oxidation states, we can't just look at it and say what it is. So we'll move on, no fluorines, no hydrogens, so we get to oxygens. Oxygen is going to be -2, so let's pop in all of those -2s. Now you can see we can easily assign everything else. For the Fe2O3, we got 3 times -2 is -6, so 2 of the ions must be 6, so the ion must be +3 there. Carbon monoxide, we got a carbon, which we don't know yet, -2 is 0, so thus the carbon must be +2. And finally, CO2, we've got the carbon +2 -2s is 0, so the carbon must be +4. Why is it a redox process? Because the iron goes from 3 to 0, which has been reduced, and the carbon goes from +2 to +4, it has been oxidized. I hope you find these are as much fun as I do. Nitrate ions can be prepared from ammonia. The first step in this process is given. Use oxidation states to show this is a redox process. Well, by now, I hope you're getting used to the whole idea. We start off by saying that the oxygen here is 0 because it's an element, and there's water plus 1 minus 2. No metals, no fluorines. We do have hydrogen, so this hydrogen will be plus 1. Pull that out, therefore, the nitrogen plus 3 times plus 1, so nitrogen plus 3 is 0. Nitrogen there must be minus 3. Already done O2, let's go to NO. Again, we've got oxygen there, which we can immediately now say is minus 2. Thus, the nitrogen minus 2 is 0. The nitrogen must be plus 2. So let's see what happens. The oxygen goes from 0 to minus 2, so the oxygen has been reduced. And the nitrogen goes from minus 3 to plus 2, an increase in oxidation state, so it has been oxidized. During the smelting of a given species, C2S is produced. This is collected and blown with air to produce copper. This is classified as a redox reaction. Use oxidation state to explain which elements have been oxidized and reduced. That's actually not true. It's not elements, it is atoms. But what the heck, let's not get too pedantic here. So looking at what we've got straight off, the oxygen is going to be 0 and this copper is going to be 0 because it's got a charge of 0. No doubt, therefore, its oxidation state is 0. Now let's go through. We've got a metal, but it's a transition metal, so we can't exactly say what it's going to be. We've got no fluorines, we've got no hydrogens. We do have oxygen here, so we'll say the oxygen's minus 2. Pull that out. Sulfur minus 4 is 0, so the sulfur there must be plus 4. Now we're left with Cu2S. Well, the copper is going to be positive and the sulfur will be negative because copper is a metal and sulfur is a non-metal. Going all the way down to rule 5, we say the more electronegative atom is going to be negative, so that's the sulfur there, and sulfur wants to be minus 2. Okay, because it's just like oxygen. If there's nothing stopping it, it will be minus 2. So that means that the copper must be plus 1. So, which atoms have been oxidized and reduced? The copper goes from plus 1 to 0. It's been reduced, therefore its oxidation state has gone down. And the sulfur has gone from negative 2 to plus 4. So therefore it has been oxidized. And also the oxygen, of course, goes from 0 to minus 2, so it too has been reduced. So in other words, you've got to reduce both the copper and the oxygen in order to oxidize the sulfur. When hydrochloric acid heated with MN2 reacts according to the following equation, why can this be classed as a redox reaction? See what we got. Can't do anything yet there, or there, or there. Chlorine, Cl2, so 2 chlorines are 0, so each chlorine is 0. And then, of course, there's the water, plus 1 minus 2 for the hydrogen and oxygens together. Right, we got metals, but they're transition metals, so we'll move on. We got no fluorines. We do have a hydrogen is plus 1. If the hydrogen in HCl is plus 1, therefore the chlorine must be minus 1. Then we've got oxygens here. Oxygen's going to be minus 2. If the oxygen there is minus 2, that means the manganese must be plus 4 to balance out 2 of the minus 2s. Now we're left with MnCl2. Let's pull that out. The manganese is more electropositive, or it's the metal, so it'll be positive. The chlorine will be negative. It's the more electronegative of the two atoms. Chlorine wants to be minus 1, unless there's anything stopping it, which there is not. So that's minus 1, so the manganese must be plus 2. Why is this a redox reaction? Manganese goes from plus 4 to plus 2, so therefore it has been reduced. And if it's been reduced, something must have been oxidized. Let's look at the chlorines. Some of the chlorines stay as minus 1, but some of them go from minus 1 to 0. Thus, the chlorine has been oxidized. Hence, it is a redox reaction. Finally, in this section, oxidation number of vanadium in VOCl3. Well, the oxygen's minus 2, so let's pull that out easily enough. Vanadium is a metal, chlorine is a non-metal. Chlorine is therefore more electronegative. It will be negative oxidation number, just as was the case up here. If there's nothing stopping it, chlorine will be minus 1. So we got the vanadium, minus 2 plus 3 minus 1s is 0. So that's minus 2 minus 3. Putting them together, you get minus 5. So the vanadium must be plus 5. Wasn't that fun? Oxidation numbers as applied pretty much to explaining why equations are redox equations, finishing off with a fun little transition metal complex.